Okay, so a few things to report. So one is directly Casper related. So Mike Stay and Tomislav and I talked through an approach to the merging of blocks that doesn't involve the tri-merge and maybe a little simpler than the tri-merge. Essentially, the idea that I threw out and then was refined by Mike and Tomislav is to, rather than, so the issue is that we have to climb to the common ancestor for a couple of blocks in order to detect conflicts. So what would be a little better is to memoize that information. So it's a kind of space-time trade-off here. We're taking up a little bit more space in order to not have to walk up the tree or the DAG, walk up the graph. So you keep a conflict set. The conflict set is really the list of COM events that might participate in conflicts. Mike further optimized this. So I was originally proposing to keep it in the blocks themselves. But Mike suggested that that isn't necessary, that they can just remain in memory because you can always calculate it. So if we keep a map from the blocks to the conflict set in memory, then you don't have to walk up the graph to do the conflict check. It does require that when you detect a conflict, especially if the conflict between two blocks, represents transactions that against the same channel, you have to pick a winner as opposed to pick an order. So what that means is that we would have to increase the collection of states associated with transactions. So you'd want a state to represent the fact that the transaction was in conflict with another transaction and was the loser, so that a client knows what to do with respect to that transaction, either to resubmit it or to tell some application that the transaction was conflicted or something like that. Does that make sense?
Yes, I'm following.
Cool. So that should make it easier to implement. I think it's a relatively straightforward task to implement that. We can always implement the tri-merge in addition, but I think the conflict set is relatively well spec'd and something that could be implemented in a much less invasive way than the tri-merge. Any questions or comments? Tomislav?
Yeah, so I'm thinking, user will detect this conflict in the later period, right? After deploy is already on another node, and so we need last finalized block as a way to decide when this deploy is definitely
Conflicted.
in
Yeah,
conflict.
that's correct. That's right.
I mean, I have one question more about implementation. Mike said that this detecting conflicts can be implemented with Bloom filter. So I'm not sure exactly what is the optimal way to implement this. Maybe this is not the question for right now, but
Yeah, oh, that's an interest. That's certainly an interesting idea, to use a Bloom filter. Um, that's actually a really interesting idea. I have to think about it a little bit more, but I like that proposal. Just to, yeah, I think that's a cool idea.
I'm thinking from perspective of blocks that we are keeping in memory, and the biggest part is event log. So I'm thinking how to not only for this purpose, but for all the other Casper stuff, we should have good caching of blocks. So if we have one block in memory, it should be only one instance, right? Because it's immutable and doesn't make sense to have multiple copies, which we have right now.
Yeah, I think that's it's certainly a good goal. I mean, I can imagine, denormalizing, so to speak, if for again, if um, if the block is a key in a map, then the map has to have then that map of would have to be accessible to all the different clients of that map. So even if the block is the key, that doesn't mean the map won't be updated, which would then mean that you would take locks to be safe in all the client usages. But you might want to look at it. I can imagine where there are situations where you don't want that structure. But anyway, it's just,
Mm.
yeah.
Okay, okay.
Yeah. It's just, that's more contingent. We need to look at the implementations and see.
Mm-hmm. Mm-hmm.
Okay. Um, so moving on. So this weekend, Christian Williams submitted a paper on using the sheaves of a theory to implement the structural types. There are several sort of questions that still need to be resolved. His presentation uses an equation for the rewrites, so that's not going to yield the semantics that we want for modalities. Um, that's not so it'll give us the structural types for a wider range of things than the distributive law would give us. He's using a topos, so the collection is still incredibly set-like. Right, so um, that's it doesn't improve it in that regard unless, well, I mean, it turns out you can build sheaves over a wider range of categories. So one of the things I've been driving is to try to do a calculation that's sheaves over, for example, a category that's a model of linear logic, some star autonomous category. So that would potentially widen the scope beyond what we have been able to accomplish with the distributive law, which would be nice. So we're looking at that, and then, but by and large, the theorem that's important here is that P and Q are bisimilar if and only if, for all formulae, um, P satisfies the exactly the same formulae that Q does, right? So that's the important theorem for these kinds of logics. And so it's going to be important to correct the semantic interpretation, but the harm that he generates is exactly the arrow the arrow definition that we give. So that's that Mike and I came up with. So that's that's very comforting, right? And this gives us more confidence that the two approaches will eventually converge. Um, so it's nice that paper has been submitted to Applied Category Theory for a talk. And then this weekend I finally took some time to look at the trace construction that I'm interested in. Still working out the details, but essentially for a trace, what you need is a family of functions for each triple of types x, y, and u. So if you have, so that takes the Hom set or the Hom gadget from x tensor u to y tensor u. So you got all the morphisms that are running from x tensor u to y tensor u, and you take those over to just the morphisms from x to y. So you can kind of think of u as an accumulator, right? So the trace is sort of tracing out the accumulator, right? So it implements a kind of convergent recursion. So if you look at what that means, so if we're treating our arrow definition as the Hom, then what we're doing is we're looking at whenever a term is of the form k. So k is our our operator that is where interaction happens, right? So k of t, like par or application or something like that. So k of t, k of some term which I'll call wx, wu, right? So there's an x part and a u part. Whenever that goes over to rewrites to some v, then the v is going to be of some form k of wy, wu. So that's essentially the rewrite that we're looking at. So we're looking at all the terms w that have this form. So then that we want to get something k of t wx goes to wy, right? So that's what we're looking at. In the setting that we're talking about, k is symmetric, or at least braided, but it's symmetric. Yeah, in all the cases that we're considering, it's symmetric. So since it has a symmetry, we can look at, we know that t, so that means that the left and the right identities coincide, essentially. So there's just one identity for k. So like 0 is the identity for par. So that's the situation that we're considering. And so you can rewrite t to k of t and the identity. And then when you look at, I think I can do this calculation on the fly here. Let me just, all right, let me scroll down to the bottom and then do a screen share. Okay, all right, so if we have x tensor u, and then this is the arrow to y tensor u. So that's going to be the set of all terms w such that there exists a t such that w is equal to an abstraction k of t and some variable. I'll just call it x. X is not the best. I don't know, z. So z is some variable, right? Typically we were using a whole, but since we're using second order theories now. And then that means that for all w prime that's typed y tensor u, sorry, x tensor u. So that's going to be of the form k of x u, right? So that's our tensor. Whenever there exists a row, the application of w to w prime that rewrites to a v. Right, so if that is around, that implies that we have that v must be of type k y u. Okay, so that's the, I'm just unpacking the definition of the arrow from the paper. So what that means is that we have some k. So remember, w is of this form. W is of this form. So when I apply, oops, k, t, z. So that's, so if I take this thing and I apply it to some w, right? So, and that w prime is going to be of the form k of, so we'll say w sub x, right? So that's the x part, and w sub u, that's the u part, right? I guess since I didn't use x, I can avoid all that. I can go x u, so that'll be a little bit simpler, right? So when I do that application, when if that rewrite exists, then v has got to be of the form k y u. So that's what that's saying, right? So we know that this application is going to be of the form k t k u. Sorry, x u. So that's our rewrite. And what we want to do is we want to get from there to here. So this is a set of different w's. So w is going to be of the form k of t z, such that for all w prime of the form x, right? So whenever I've got an x, right, then the existence of a rewrite from w at w prime over to v implies that v is of type Y. Oops. There we go. Okay. So what that means is K of T X goes to Y. Does that make sense? So we're trying to, so knowing this, we want to get to that. Now, we know that since this is symmetric, L is equal to R. So the left and right identities for K are the same. And let's just write that as 1. Okay. So then we know, therefore, that T is equal to K of T1. Does that make sense?
Yeah.
Okay, cool.
This is like something with in row, something in par with nil.
That's correct. That's exactly right. That's exactly right.
Okay.
Okay.
Can you just explain the at sign in the syntax?
It's just
This is
application. It's application.
okay.
So
Like on the application on the term level, and a row is on the type level.
yeah, so we can,
Is,
row is a rewrite. So it's a rewrite from a term to a term. So let me rewrite, this might be a little simpler, lambda z dot, and then here, lambda z dot. Okay, so there's our lambdas. So now I'm applying a lambda to a value, right? And just replace the z with the value. That's all we're doing. All right, so we know that if I have k of k of t 1, k of, oops, yeah, k of x u, right? So if we were to cut this, right? So if we cut this, then this would have formed. So let me do this to indicate that we're not talking directly about a rewrite. So then this would have, the cut would have been k of t x come on fingers, and k of 1 u, right, which we know to be the same as k of t x u, and right, and likewise we can go from the other side, right, and we can get, if we cut in the other way, right, so we do the identity on the left, then we get k, here, let me do it this way so we can compare visually. If we go the other way, so then we get which is equal to k of sorry, of x, k of t coming. So that's the, and so what we want to do is to take advantage of this and some other things to essentially go around the loop so that, you know, if we, if the U part, so essentially what we're trying to do is to show that we can't, we can't interact directly. Well, how do I say this? Yeah, that's right. That's right. We can't interact directly when we have something of this form up here, right? We have to break this down into components. Okay, so that's the trick. So T is going to have to interact with X, and that's going to have to interact with U. And so if there's any U left over, so we keep going around the loop with U until until we get into Y. That's essentially, so if T interacts with X and just produces a Y, we're all good. If there's any U left over, right? So in this case, there's some U left over. So we want to get rid of that U. So we want to go around the loop again and again until we get rid of the U. The U is essentially evaporates and we just have a Y. So the linear combinatory picture is this one. Right, so if we come in on the X side, right, and so T will interact with X. If that produces a Y, we just come out the Y. If there's any U left over, we want to interact with the U again and again until we get rid of the U and then pop out of the Y. So that's essentially essentially what's going on, right? That's, so I'm sort of honing in on the bits and pieces that we need in order to construct that loop. So I'm not quite there yet, but I'm sort of being suggestive with these two observations, right? So that's the work that's ongoing to build out the trace.
And the U is constructed after the X have interaction with T. The first interaction.
Right. So in order to do any kind of interaction, this has to be decomposed essentially. Well, there are two ways to do it, right? You can either reduce this way. So you can reduce this with this and this with that, or you can reduce this with this and this with this, and then reduce those pairs. So those are the two different ways you can construct it. You can wire it in series or wire it in parallel. So that's the idea. Since we're interested in getting this kind of thing, right, we want to, ultimately, we want to eliminate the contribution of U, right? That's what we're constructing. So U becomes entirely internal. We're tracing over that. That's the idea. All right. I have to jump off, but I'll see some of you. I think we switched the dev stand up to
Yeah.
the Rouse Room for this Monday. So I will see you guys over there.
Great.
Thanks.
Thanks, Greg. We appreciate it.
Thank you.
Yep. Have a great day.
Thanks.
You too.
Bye.